So welcome to the online Spintronics seminar number 112. Our speaker today is Professor Xufeng Zhang from Northeastern University. He has received his PhD in electrical engineering from Yale University in 2016 and was awarded the Henry Prentice Becton Graduate Prize for exceptional research achievements. After graduation, he joined Argonne National Lab as a Nikola Tesla named postdoctoral fellow and was promoted to an assistant scientist in 2018. Then in 2022, last year, he joined the Department of Electrical and Computer Engineering at Northeastern University as an assistant professor. And he has diverse research interests in device physics and applications, with a focus on experimental study of spin wave dynamics and magnonic devices that are hybridized with microwave, photonic, and mechanical components for coherent and quantum information processing. Dr. Zhang has published over 50 peer-reviewed research papers, and his pioneering works on magnon and photon coupling are among the first experimental demonstrations of hybrid magnonics, which will be his topic today. Dr. Zhang led multiple research projects funded by DOE, DARPA, and NSF, and he's also the recipient of the 2023 Young Investigator Award from the Office of Naval Research. Everyone, please make sure your microphone is muted if you're not the speaker. And Xufeng, please go ahead with your talk. I look forward to it.
Okay, thank you, Kirill, for the nice introduction. And I would like to thank Xin and other organizer of this seminar for giving me this good opportunity to present my work. And today I'm going to talk about our recent work on controlling the hybrid magnonic interaction. So here the content of today's talk. I will start with a brief introduction. Then I will talk in details about the manipulation of cavity electromagnonics in both quasi-static situation and real-time control. At the end, I will talk about the perspective for the future research directions in this research area, and I will end my talk with a conclusion and acknowledgement. So let's start with the introduction. Actually, let me start with something that's really fundamental, really basic. I suppose everybody here is very familiar with this concept, but just in case, bear with me to go over this very briefly. So we know magnons are the quantization of spin waves, which is a collective excitation of magnetization. In a magnetic ordered material, the spins can be perturbed and then precess about its equilibrium position. And this precession can propagate from one spin to the next, form a wave-like motion, as shown in this cartoon here. And also, there are a lot of materials that can be used to excite or support the magnon. And shown here in this list, just a few examples, including thick yttrium ion garnet or YIG films, also thin films for YIG, also permalloy and other magnetic alloy and compounds. And among all these common magnonic materials, the most popular one so far is YIG, because as you can see from this list, it has the lowest magnetic damping. And but on the other hand, YIG has another problem. It's very, very strong, very tough material to work with. So making micro or nano devices out of this material is extremely challenging. That's why people are also very interested in other materials such as permalloy, which has a higher loss, but much easier fabrication and process capability. We know, just like photons, magnons can be used to carry or process information. And shown here are just a list of few examples of the active research areas related to magnon-based information processing. So we know magnons have a lot of unique properties. For example, it has a very large frequency tunability that can cover gigahertz to terahertz range. Also, it has intrinsic reciprocity. Its wavelength is much shorter than the electromagnetic waves of the same frequency. So there are a lot of different possibilities for using magnon to process coherent information. For example, magnons can be used to study novel physical phenomena such as Bose-Einstein condensate or supercurrents, or topological phenomena such as skyrmions. Also, magnon can be used to real practical devices such as magnetic memories, magnon logic, RF components, or non-reciprocal devices such as circulator isolators. The study of magnons also includes the propagation and the damping mechanisms of the spin wave. And in recent years, there are a lot of effort in exploring novel materials for magnonic systems, such as anti-ferromagnetic materials, topological insulators, while semi-metal or 2D materials. And among all these possibilities, there is a emerging research area called hybrid magnonics in recent years that has been gaining a lot of attention because of its unique properties. And that will be the topic of today's talk. So what is hybrid magnonics? So basically in hybrid magnonics, we hybridize magnons. And we know, in addition to magnon, there are many other kinds of coherent information carriers, such as optical photons, microwave photons, mechanical phonons, other forms of magnons, or even quantum defects. So in principle, magnons can be hybridized or coupled with all of these different systems. And the idea of hybridizing magnons with other information carriers is to combine the advantage of different systems, because we know each system has their advantages and disadvantages. For example, magnons is well known for its large tunability in frequency, but it also suffers from relatively short lifetime, which is usually on the order of a microsecond or even nanosecond. That's pretty short. While on the other hand, for phonons, they can be engineered to have very, very long lifetime on the order of a millisecond or even longer. But in the meantime, you also suffer from very small bandwidth. So bandwidth. By combining or hybridizing magnon with phonons, in principle, we can make a highly tunable but yet long-lived memory, for example, for quantum applications. So that's the benefit of hybridizing different systems. And the beauty of a hybrid magnonics is that we can hybridize one magnonic device with multiple different systems simultaneously on a single device. And in this manner, magnonic devices can be used as a transducer to connect all different kinds of coherent information processing platforms. And although magnon can be hybridized with different systems, the coupling strength between the magnon with different information carriers are different, as indicated by this yellow polygon here. So for example, for the optical photon and the spin, their coupling with magnon are relatively small, while the coupling between magnon and the microwave photon are very, very strong. This coherent coupling can be characterized by a property called cooperativity, which we will talk just in a few minutes. So as you can see, magnons can be used to hybridize with different coherent information carriers. And depending on which information carrier we hybridize with, we will end up with different hybrid magnonic systems. For example, when hybridizing magnons with optical photons through magneto-optical effect, such as a Faraday effect, we can have this so-called cavity optomagnonic systems. This cavity optomagnonics is an analogy of cavity optomechanics, if you're familiar with that system. We know cavity optomechanics involves a coupling between optical photon and mechanical phonon, and they have been gaining a lot of attention in the past few years because of their excellent performance in quantum information processing. In principle, cavity optomagnonics can do the same thing, but right now we're still limited by the finite device performance. And there have been a lot of efforts in trying to further improve the current optomagnonic device performance as of now. On the other hand, if we can couple magnons with mechanical phonons, we will have this cavity magnon mechanics. And in this way, the coupling is through a magnetostrictive effect. And here, the mechanical mode can have a frequency at the same range as the magnon mode or at lower frequency. And depending on the different frequency configuration, the interaction mechanism might be slightly different, but they will always be through this magnetostrictive effect. And the coupling or hybridization between magnon with microwave photons will give us this cavity electromagnonics. This is by far the most intensively studied hybrid magnonic system, because the magnon coupling with microwave photon is the strongest, which is through the magnetic dipole-dipole interaction. And in this case, the microwave photon and the magnon are both in the gigahertz or tens or hundreds of gigahertz frequency range. And so this cavity electromagnonics can be further extended to couple with superconducting qubits. In this way, the magnon can couple with the superconducting qubits aided by the microwave photon. And this will give us the quantum magnonics. So far, hybrid magnonics have found a lot of different applications. For example, in quantum magnonics, people have demonstrated the quantum magnonic state in a macroscopic object with a dimension on the order of a millimeter. This is something really incredible. And by combining cavity optomagnonics with cavity electromagnonics, we can, in principle, build a quantum transducer that can convert quantum information from a microwave frequency, where the superconducting qubits operate at, with the optical photons, where we have the long-distance quantum communication links. And also, hybrid magnonics has been used for dark matter detection, because it has a very large frequency tunability. So this will increase the bandwidth of these dark matter detectors to accelerate the detection process or search process for dark matters. So as I mentioned earlier, the coupling between magnon and microwave photon is strongest. That's why cavity electromagnonics has been gaining the most attention nowadays. And that's why we're going to talk about this part today. So in principle, this cavity electromagnonics can have a lot of different implementation forms, but no matter how complicated this system may look like, they can always be simplified into this simple model. Here we use A to represent the microwave photon, which is at gigahertz, and M to represent magnon, which also at gigahertz. Both photon and magnon have their dissipation rates indicated by kappa A and kappa M for photon and magnon modes. And their coupling can be characterized by the coupling strength G. The interaction Hamiltonian between the magnon and the microwave photon can be described by this beam splitter type Hamiltonian. As you see, H bar G multiplied by A dag M plus A M dag. So this indicates the annihilation of one particle or quasi-particle is always accompanied by the creation of another particle or quasi-particle. So this allows coherent information conversion from one particle or quasi-particle to the other. And depending on how strong the coupling strength is relative to the dissipation rates, we have different coupling regimes. For example, when the coupling strength is smaller than both dissipation rates of the magnon and the photon modes, we are in the weak coupling regime. And in this regime, the system dynamics is dominated by the exponential decay, and we will not be able to see any interesting coherent information exchange between magnon and the microwave photon. So this is not very interesting. But if we can increase the coupling strength G to be larger than at least one of the two coupling strengths, the dissipation rates, we can get to the EIT, or electromagnetically induced transparency regime. And if we can further increase the coupling strength G to be bigger than both dissipation rates, we enter the strong coupling regime. And in these two coupling regimes, we are going to have system dynamics other than the simple exponential decay. So this will correspond to the coherent information exchange between magnon and the microwave photon. And the coupling between the magnon and the microwave photon can be characterized by this parameter called cooperativity, C, which is defined as a ratio of the square of the coupling strengths over the two dissipation rates, which is dimensionless. And usually for coherent coupling, such as EIT or strong coupling, we want this coupling cooperativity C to be larger than 1. So in today's talk, we're going to focus on the strong coupling regime because it has the best coupling among all the 3 coupling situations, and you will have the richest coupling dynamics. So shown here is a typical reflection spectrum from a cavity electromagnonic system. So here's y-axis is a frequency, while the x-axis is a bias magnetic field that is used to support the magnon excitation. So as you can see here, we have this horizontal line that represents the microwave resonance, the photon mode that does not change with bias magnetic field. While this tilted line here is a magnon mode that has a frequency linearly proportional to the bias magnetic field. Here we're using the ferromagnetic resonance or FMR mode of the magnon mode, so we have this linear dependence. So when the bias field is small, the magnon frequency is far away detuned from the microwave photon frequency. So if we draw a line here, we see only a single reflection dip that corresponds to the absorption from the microwave photon resonance. But if we change the bias magnetic field such that magnon mode has a frequency the same as the microwave photon mode, we will see the two new normal modes forms because of the coupling between the magnon and the microwave photon. And as a result, in this spectrum, we see this anti-crossing, or sometimes called level repulsion here. And previously, in the case where the magnon is detuned from the cavity photon, the system dynamics, when we measure it after sending in a microwave pulse, we will see the system, the reflection from the system will show a exponential decay. Note here, the y-axis is a log amplitude. So this straight line indicates exponential decay. So nothing interesting. But when we have this normal mode splitting, when the magnon mode and microwave photon mode is strongly coupled, we can observe this rabbit-like oscillation, indicating the coherent information exchange between magnon and microwave photon. So here at the tip, at the top, we have the all energy in the microwave photon mode. So when you measure the cavity reflection, you have the maximum amplitude. But when we get to the dip, the bottom of this curve here, all the energy is converted from the microwave photon to the magnon mode. So that's why when you measure the cavity reflection, you don't see much signal over there. So you see a dip. And this back and forth oscillation indicates the information exchange between the two modes. And the oscillation period, T here, is inversely proportional to the coupling strength G. Therefore, by increasing the coupling strength G, we can make the period much smaller. That means we can have more oscillation periods within the finite magnon lifetime, or magnon or photon lifetime. So this will allow us to have more coherent operation within the finite lifetime. That's why people have been working very hard to push this coupling strengths. So this is a basic model of this cavity electromagnonics. There have been a lot of efforts recently in trying to explore different properties of this cavity electromagnonics and their potential applications. As I mentioned, one big effort people have been doing is to enhance the coupling strengths. For example, by using this sandwich layer, superconducting and magnetic layer, people are able to enhance the coupling strengths significantly. Also, by using a Higgs sphere to serve both as a microwave cavity and the magnon resonator, we can also greatly enhance the mode overlap between the two modes, the magnon and the microphoton mode, which also significantly enhance the coupling strengths between the two modes. And so far, people have achieved the coupling strengths that is more than 25% of the resonance frequency. So this is really large coupling strengths. And this is called ultra strong coupling regime. And in this regime, a lot of interesting phenomena will show up. And right now, people are trying to further push the coupling strengths to be comparable to the resonance frequency of the cavity, photon, and magnon mode, which is called a deep strong coupling regime. And another interesting phenomenon people have been exploring is the so-called level attraction, as opposed to the level repulsion we talked earlier. As you can see here, the two levels are attracted and form a single level here in this spectrum. And this is achieved by introducing the dissipative coupling between magnon and the microwave photon. And there have been a lot of effort recently on this direction too. Also, another interesting property of this hybrid magnonic system is the non-reciprocity. We know magnon as a magnetic excitation. In principle, we can use it to break the time reversal symmetry and achieve non-reciprocity. However, in most of the previous demonstration of hybrid magnonics or cavity electromagnonics, the system is reciprocal. But here, by introducing dissipation engineering and the coupling strength engineering, people were able to achieve non-reciprocity and even unidirection invisibility in hybrid magnonic systems. Another direction of recent research is on the non-Hermitian physics. We know in the hybrid magnonic system, there are a lot of tuning parameters we can play with. So this gives us a lot of flexibility in the system configuration. And as a result, a lot of interesting non-Hermitian phenomena can be demonstrated on such a hybrid magnonic system, such as perfect absorption, exceptional points, or even exceptional surface. And another very important research efforts in hybrid magnonics is on-chip device integration. Most of the previous demonstrations are using bulky devices such as 3D microwave cavities or X-spheres that has a dimension on the order of a millimeter or even centimeter. That's not ideal for future integrated system development. So there have been great effort in trying to building integrated magnonic devices that is hybridized with on-chip superconducting resonators or other forms of on-chip devices. Among all these research efforts, another very important thing that is needed is the control of the coupling strength or the coherent hybridization process. More specifically, we want to control how strong the magnon and the microwave photon are coupled, or how or when to start and stop the coupling between the two modes. And that is what I'm going to talk about in the next. So, which is a manipulation of a cavity electromagnonics. And we're going to talk about two different cases, the quasi-static tuning and real-time control. Let's start with the quasi-static control. So this is the device we use for this control. It's made of a printed circuit board, a piece of a PCB with a high dielectric constant material sandwiched between two copper layers. And on the four walls, we use silver paste to enclose, to seal all the four walls. And as a result, we have a 3D cavity, miniaturized version, because we have very high dielectric constant material inside. So the dimension is much smaller compared with the previous 3D microwave cavity we used earlier. And on such a cavity, we can drill a hole to put a microwave connector to excite and detect the microwave mode inside. And then on the surface, we can make a slot to expose the interior of this microwave cavity. And then we can put a sphere into that small slot so that the magnon mode can interact with the microwave photon mode inside this cavity. Although this slot will make this cavity very leaky, this will increase the microwave photon resonance line width, but the coupling strength is also very large because of the confined microwave field by this dielectric material. As a result, we're still able to achieve strong coupling between the magnon and the microwave photon, as indicated by this anti-crossing feature as shown in this measured reflection spectrum. And from this spectrum, we can extract the coupling strength G, which is 128 megahertz. And as a comparison, we have the dissipation rate for the magnon to be 1 megahertz and for the photon to be 54 megahertz. Both are very much smaller than the coupling strength. So this confirms we can still achieve strong coupling. And on such a device, we want to show our controllability on the coupling strengths between the magnon and photon modes. And let's take a look at how many parameters we can tune, or how many tuning knobs we have. So here shows our device. So we already know that the magnon frequency can be tuned by a biased magnetic field, which is generated by a small coil, the coil current. And again, because we're using the FMR resonance the mode of the X-sphere, its frequency is linearly proportional to the biased magnetic field. And the other parameters we can tune is the position of the X-spheres, both in the X and the Y directions. Also, the angle of the biased magnetic field to the surface of this resonator, as indicated by this angle theta. And all these three parameters here can be used to control the coupling strength G. For example, we know inside the slot here, the microwave magnetic field is not uniform. Instead, it has a distribution, spatial distribution, that is a function of X and Y. So that means when we move the X-sphere around inside the slot, it will feel different cavity field. And as a result, the coupling strengths between the two modes will be different. As shown in this plot, which is a measure of the coupling strengths as a function of the X and Y positions. And you can see this surface resembles the distribution of the cavity field distribution. And in addition to the X and Y, changing the angle theta also changes coupling strengths that we can achieve. Because we know in order to have the magnon strongly coupled with the cavity photon, we need the biased magnetic field to be ideally perpendicular to the magnetic field of this cavity resonance. Because in that case, we have the maximum torque between the two magnetization and accordingly the largest coupling strengths. If we align the biased magnetic field H to be in parallel with the microwave component, the magnetic component of the microwave field, the torque will be zero, and the coupling between the magnon and the photon will also be zero. So shown here in our measurement, indeed, by changing coupling strength, by changing the angle theta, we can change the coupling strength in a quite big range. Now we have 4 tuning parameters that can control 2 properties: the magnon frequency and the coupling strength. This allows us to observe some interesting phenomena. For example, we can observe this exceptional point in our hybrid magnonic system. An exceptional point is a singularity point in the 2D parameter space. So as you can see, since we have 2 coupling modes, if we solve our system, we will always have 2 eigenmodes and 2 eigenvectors. However, there's one exception, which is this point, the exceptional point. At this point, both eigenmodes and eigenvectors coalesce. So we have only a single eigenmode and a single eigenvector at this point. So this point, that's why it's called a singularity point. It's very different from any other point in this 2D parameter space. And this point can be obtained when the coupling strength G matches this condition, and the coupling, the detuning of the magnon with the cavity photon should be 0. So shown here is the constructed Riemann surface from our measurement results, and we indeed observe this exceptional point in our hybrid magnonic system. And the reason exceptional point is interesting, we want to study that, is because you have a lot of novel properties. For example, at this exceptional point, people have demonstrated enhanced sensitivity because there is a quadratic dependence of this eigenfrequency as a function of the system parameter, which will give us much higher sensitivity when the system parameter has a small, very small perturbation. That's shown in these 2 Nature papers originally. And not only at this exceptional point, there's some interesting properties around this point. For example, if we encircle this exceptional point, we will have topological mode conversion, as shown by these Nature papers. In this way, you can obtain topologically protected, robust mode conversion between 2 modes, and you can also achieve some so-called chiral mode conversion So the final state only depend on which direction you encircle this exceptional point. It does not matter which initial state you have. So this is very interesting and useful for practical signal processing as well. But in our hybrid magnonic system, we can do something even more than this. Because our system has a lot of flexibility, we have a lot of tuning parameters we can play with. So in addition to single exceptional points, we were able to observe a collection of exceptional surfaces as indicated by these measurement results, those dots. So these dots form a 3D surface in a 3-dimensional parameter space. And this high dimensional collection of exceptional surface is first demonstrated experimentally in our system. And more interestingly, here we also observe this so-called exceptional saddle point. And this is even more interesting compared with normal exceptional points, because at this point, if we measure the frequency and line width of this our eigenmode, you can see the two quantities have different dependencies on 3 different system parameters. So that means in principle, we can make a sensor using this exceptional saddle point that can simultaneously detect the 3 different system parameters. So this is so far what we have obtained on controlling the coupling strength between magnon and microwave photons. Although interesting phenomena have been achieved, but there is one very significant limitation we cannot ignore here. All this control we have done so far is static. That means the tuning of the coupling strength will take place in the time scale that is much longer than the magnon and the photon lifetime. That means within the finite magnon photon lifetime, the coupling strength is still fixed. So to solve this problem, we have to find a way to do real-time control, because we know for a lot of coherent information processing, that is how the information is processed. We're limited by the finite lifetime. There have been a lot of attempts in achieving real-time magnon photon coupling control. And for example, in this science paper from Nakamura's group, where they demonstrated the coherent coupling between magnon and superconducting qubits, and they even demonstrated the quantum state in the magnonic resonator, they were able to control the dynamics between the magnon and qubit coupling. However, this control, it actually depends on the tunability of the qubit. So that means it cannot be generally applied to any hybrid magnonic systems, because most of the system does not have a qubit to control. Well, in this work, people have sent in a microwave signal to control the coherent dynamics between the magnon and the microwave photon. For example, they can turn off and turn on the coherent oscillation between the magnon and microwave photon mode. But the problem is that here the control has the same frequency as a target signal. So that means it's impossible to separate the control with signal, and this makes it quite challenging for real signal processing. So our goal here is that we want to demonstrate the in-situ and on-demand tunability of the hybrid magnon and photon interaction. And there are 2 approaches. The first one is to control the detuning frequency. So if we go back to the model of the magnon and the photon hybridization, we see in addition to the dissipation rate and the coupling strength, actually there is one additional parameter we ignored earlier, which is a detuning frequency between the magnon and the photon mode, delta F. Recall that we have this Rabi-like oscillation when the magnon and the photon is on resonance, or in other words, the delta F is 0. If we can control the delta F within a certain period of time, for example, here, we can control the oscillation period and this extinction of this oscillation. If we can further increase the detuning delta F to be very, very large, in principle, we can completely stop this oscillation. So that means we can stop the information exchange between the magnon and the microwave photon mode, and then we can turn it back on. this is the kind of tunability we would want. And everything occurs within the finite magnon lifetime before the energy is totally dissipated. But the challenge is that this kind of detuning is usually realized by controlling the magnon frequency, which is controlled by a biased magnetic field that is provided by a permanent magnet or electromagnet. All these magnets have very slow response speeds, as we know. So in order to make this tuning in real time, we have to find a way to have a fast response for these magnets. So shown here is the device that we used. So it's a dielectric resonator placed in the metal housing, and we have a loop probe to measure the cavity reflection, and we have a sphere placed underneath this dielectric resonator, and by placing them close to each other, the magnon and the microwave photon in the dielectric resonator will couple with each other. And the interesting part about our device is that we have one additional control loop surrounding this sphere, and the loop direction is parallel to the biased magnetic field. Therefore, if we send in a DC current, it will generate a magnetic field that is along the same direction as the biased magnetic field. So it will modify the biased magnetic field, and also it modifies the magnon frequency. So shown here is a cavity reflection spectrum. We see this anti-crossing again. Here we have two magnon modes, but let's focus only on the fundamental mode M0. And if we draw a cut line here, we see when the two modes are hybridized on resonance, we have this normal mode splitting. But when we send in a DC tuning current, as indicated by this voltage here, we will change the magnon frequency, which in turn changes the normal mode splitting here. And this is still DC tuning. If we can send in the DC current in a pulsed mode with amplitude changing from positive to -5 volt, we can measure the cavity reflection, for example, at this frequency, and we see it can respond in a pulsed manner. So that means our system can respond to this pulsed tuning. So that's good. That's what we want. And then let's study how this tuning speed will affect our system behavior. Shown here is the normal mode splitting again. So at the beginning, let's set our system biased under this condition, where the magnon is far detuned from the photon. So by sending in a microwave photon pulse at this frequency, we will excite only the photon mode, not the magnon. And the energy will not be exchanged between magnon and the photon because the magnon is far detuned. Then we apply this tuning current gradually, which will change magnon frequency from this point gradually to this point and to this point. And along the way, the system configuration changes, and also the system state will change. So there are two possibilities for the system to evolve. One possibility that the state will gradually change from S0 to S1 when this ramp up speed is very slow, and then we will end up with a magnon state. And then if we keep this transition to be very short, another possibility is that the state will change from S0 to S2 through path T2. In this way, the system stays in the photon mode, and the energy will be stayed in the cavity instead of being exchanged to the magnon. And if our transition is somewhere between these two extreme cases, we'll have some probability for the system to stay in S1 and some probability for the system to go to S2. And shown here is measure the probability for the system to stay in the photon state, S2, as a function of transition time. As you can see, when the transition time is really short, the photon state will remain after the transition. So that means we can change the system configuration without changing the system state. So that is good, because what we're going to do is the next. We still set our system originally in a state where the magnon is far detuned from the photon. So we see only a single resonance tip, that's a photon mode. Then we send in a microwave photon to excite the photon mode only. And then we gradually increase the system, the bias current to change the magnon frequency from here to here, where the magnon becomes on resonance with the microwave photon by the end of this ramping. And then remember, our transition is really fast right now. So after this transition, the photon still remains in photon state. However, right now, there will be non-zero coupling between magnon and the microwave photon. So the energy in the photon will start to convert to the magnon mode. And then we will start to see this coherent information, the oscillation between the two modes. And we let the system stay there for a while. Then we ramp the current back to tune the magnon frequency back to this frequency to cut off this coupling between the two modes. And depending on how long we keep the system in this state, we will end up with different final states, as shown here. For example, here, when we use we keep the system there for about 100 nanoseconds, we will end up with all the energy converted from the photon to the magnon mode. So basically, we're flipping the state in this block sphere from this pole to the other. So this is a pi pulse. And if we keep the pulse length to be half of this length, we will get half a pi pulse. And then the final state after this half pi pulse will be the superposition of the magnon and the photon mode. So we have 50% magnon, 50% photon. And now we have a pi pulse. We have a pi pulse. We can do even more complicated pulse sequences. For example, we can use 2 half pi pulses with a tunable delay tau. And in this way, we can achieve these remedy interferences. And as shown by these beautiful interference fringes. We can also apply 2 pi pulses delayed with a time tau. So the first pi pulse will convert all the information from the photon to the magnon mode and let it stay there. And then the second pi pulse will convert the information back from the magnon to the photon mode to read it out. So it's like a memory with a controllable readout. So this is the first approach to control the magnon dynamics. Right now, we have demonstrated the principle, but the device performance is still limited by the finite control strengths we can apply in our system. Now let's explore another possibility to control the magnon-photon hybridization, which is to control the coupling strength directly. Again, we have this rabbit-like oscillation when we have a certain coupling strength. So if we can control the coupling strength to make it a different value, we can control the oscillation period between the two modes, magnon and photon modes. And if we can reduce the coupling strength to be 0, in principle, we can completely cut off the energy exchange between the two modes. And then we can control how the signal couple from the magnon mode to photon mode, or to turn it off, then enable that again. This sounds interesting, but the problem is that in most of the hybrid magnonic systems demonstrated so far, this coupling strength is usually determined by the device geometry and the configuration, so it's semi-static. It's impossible to tune the coupling strength within the finite magnon and photon lifetime. To address this challenge, we use this same device, but now this time we're sending in a AC drive to our this control loop instead of a DC current as we used earlier. So in this way, before we sending in an AC drive, we have the normal mode splitting when we put the magnon to be on resonance with the microwave photon. And then a AC drive will be sent in to such that the driving frequency match the frequency difference between the two normal modes. So in this case, if we look at the energy diagram, energy level here, we'll see magnon and the photon mode interaction will give us two normal modes, D minus, D plus. Right now, we can effectively treat this one as a two-level system. Now, when applying a drive between these two-level system, we know this will induce secondary splitting for each level. This is similar to the autoautonomous effect in the atomic physics. And this secondary splitting can be controlled by the strength of this drive here. So it is really important. So different from previous magnon photon hybridization, right now we have a coupling strength that can be controlled by electric signal. That means we can control this on and off of these two energy levels, or the creation of this secondary splitting here, simply by changing the driving signal amplitude. This is good. And right now, the interaction Hamiltonian is a little bit more complicated than before because we have this additional driving term here. And shown here is a measured secondary splitting and the different driving amplitude. As you can see, with increasing driving amplitude, we can get a larger and larger secondary splitting here. And if we summarize everything in this 2D map, we can see the original two energy level, D minus, D plus, will split in this way. And we get a coupling strength of 6 megahertz, 2G equals 6 megahertz, and which is larger than the magnon and photon line width. So we're in the strong coupling regime. And shown here is basically this cartoon gives you a better idea what happened. So the drive generates a sideband, and with sideband goes to the other branch. You will push the other branch away instead of simply crossing it. So that's how we get this the secondary splitting here. And shown here is a measured reflection spectrum as a function of driving frequency. And as you can see, this secondary splitting only occurs when the driving frequency match the original level spacing between the two energy levels, which is about 27 megahertz. And if we study the system dynamics, in this case, when there's no secondary splitting, we see the original Rabi-like oscillation with exponential decay. But if we look at the system dynamics, when the secondary splitting is present, we will see, in addition to the Rabi-like oscillation, we have this some kind of retrieval process indicating the effect of this secondary splitting here. And shown here is what happens for this secondary splitting, the flow key drive, when the magnon have different detuning as the microwave photon. As you can see, when the magnon frequency gets closer to the photon frequency, this secondary splitting gets larger and larger. But in principle, we can get this secondary splitting anywhere for any detuning when it's not too large. So this kind of so-called orthogonal splitting has been previously demonstrated in photonic system, where people use these coupled lithium niobate photonic resonators to develop a programmable photonic molecule. In this way, the two optical resonators are coupled and forming two hybrid modes. And then by sending in a driving signal, which modulates the optical resonator frequency through the piezoelectric the electro optical effect in lithium niobate through these electrodes, this secondary splitting occurs. And they were able to build a controllable pulse storage in such a system. In principle, we can do the same thing in our magnonic system, but right now we're still limited by the finite tuning driving amplitude. But our system can actually do a little bit further than what has been demonstrated so far. So let's see what happens when the coupling strength is increased further. So this is what we measured so far. It seems like this splitting is like two straight lines, and one may expect something like this when we further extend the coupling strength, driving strength. But from our theoretical calculation, you see actually that's not the case. Instead of being a straight line here, we actually have this Bessel function shape. And the reason we're seeing a similar straight line is because we're only measuring a very small driving amplitude within this small range. So in our experiment, we're able to optimize our device and further increase the driving amplitude. And this is what we measured. And as you can see, it indeed reproduced what we theoretically predicted. So confirming the validity of our theory analysis and understanding. To better understand this situation in the strong coupling regime, this strong driving regime, let's take a look at this energy level diagram again. So this is what we had earlier. And this process can be understood in this way. So this lower energy level, D minus, will couple or will absorb one driving photon and become a higher band mode. And but when the driving amplitude increases, this secondary splitting might be larger than the original level spacing between these two levels. And as a result, you see these two energy level may exchange order. And this regime is called the flocate ultra-strong coupling regime. And in this regime, we actually have a more complicated situation than this single, this absorption of a single driving photon. Instead, this low energy excitation will absorb two driving photons and emit one to become a high energy level excitation. And in principle, there can be even high order processes, say by absorbing 3 and emit 2 when the driving amplitude is further increased. So this multi-photon process will make the whole system dynamics more complicated and interesting. So this is what we have demonstrated so far. But as you can see right now, we're still limited by the finite driving amplitude or tuning amplitude. So the system performance is still limited for practical applications. So for the future, one way to improve the device performance is to enhance the temporal control. For example, by finding a way to further amplify the driving signal, or to for example, by integrating our device with other materials such as multiferroic or piezoelectric materials, by to have a more higher coupling efficiency between the driving signal and our magnonic device. And also, as you can see, the device demonstration are based on bulky Xufeng devices. So it is desirable to achieve on-chip operation. In principle, the demonstration proof of principle we showed so far can be directly applied to on-chip devices, but the challenge is how to make on-chip devices that have this kind of enhanced, strong tunability. And also, our demonstration are all at room temperature in the classical regime, so it also desirable to achieve cryogenic operation and even in the quantum regime. And in principle, what we have demonstrated so far can be readily applied to that regime. The challenge right now lies in how to make those quantum devices that operate in the cryogenic environment with good quality factor. And with that, I'm running out of time. I'm going to stop with this conclusion. And I would like to thank my collaborators, especially my theoretical collaborators from Professor Liang Jiang's group in Chicago. I also want to thank the funding agency. And at the end, I want to make a hiring announcement, advertisement. We have postdoc and PhD student positions in our group right now. Anybody who's interested, or if you know anybody who's interested, please feel free to shoot me an email. And with that, I want to stop my talk and answer any questions you might have. Thank you.
Thank you very much, Xufeng, for this great talk. Please use the reactions buttons to thank him for his presentation. So we can now take questions. If you're in Zoom, please use your raise hand feature, and I'll invite you to ask a question. If you're watching on Twitch, you can just type the question in the chat box. So Alexei Kovalev, you have a question?
Hi, thank you for a nice talk. So I have a question. So when you mentioned cooperativity, you prescribed how to calculate it. So for a qubit, we have T1, T2 times characterizing a qubit. For magnon, we have lifetime, and also we could in principle talk about dephasing time. So when you calculate cooperativity, which time do you use, and what would be a reliable way then to calculate cooperativity?
Yeah, thank you. That's a really nice question. I guess right now we are limited by the T1, the decay of this magnon, because right now the best magnon lifetime demonstrated experimentally, I think, is still on order for probably less than a microsecond, and mostly that's because of the absorption in the material.
But for quantum operations, you will need to also control dephasing time, because you will lose quantum information.
Yeah, but I guess right now we're still limited by the absorption. We have not go to the regime that we probably have to worry too much about the dephasing at this point yet.
But you kind of also demonstrated some kind of quantum operations where you almost try to perform some kind of gates, or not yet?
I think we're still several steps away from that.
Okay, all right. So,
Yeah.
okay,
Yeah.
okay. Thank you.
Thank you.
All right, thank you. Further questions, please. Just use the raise hand feature in Zoom. Let me ask about those exceptional points and planes. So is it the point where the coupling vanishes by symmetry, or is there some other reason?
Oh, it's not the coupling that vanishes. It's a coupling reaches a certain non-zero value. You still have a non-zero coupling. It just I mean so I mean to understand this exceptional point, it's better to look at this this Riemann surface. So you will see the coupling strength. Yeah. So here, this Y position actually is the coupling strength. And when how to say that? So the coupling strength has to compensate the dissipation difference between the two modes. Yeah.
I see.
So this corresponds to the boundary between the PD symmetry and the PD symmetry broken regime.
Okay.
So yeah, so basically, the short answer is that you need a non-zero coupling strength.
You need non-zero coupling and dissipation.
Yes, that's right.
Okay. All right. Thank you. So there's a question from Shen in chat. Can the Outler-Town splitting be understood as similar to paramagnetic pumping in terms of its mathematical modeling?
That's a good question. I think for parametric this pumping, usually the pumping frequency is quite high, right? Like on the order for the magnon frequency or twice of that frequency. And here the driving frequency is much lower, on the order of megahertz or tens of megahertz.
So it's just on the order of the level splitting here.
Yeah. So in that way, so we're basically modulating how fast, how the magnon or the spin precesses in a relatively slower speed. Yeah.
Okay. All right. Sitaram, you have a question, please?
Well, I think it's interesting that there's a professor at University of Arizona who has exactly the same name as the present speaker. Do you know him?
I don't know him personally, but I heard about him. It's not exactly the same, but very similar thing.
I think he was actually on the Zoom call earlier.
Oh, really?
He used to be at the University of Missouri Columbia before moving to the University of Arizona.
Okay, Sitaram, do you have a physics question?
No.
Okay. Any other questions? Let me check Twitch. Okay, so it looks like, yeah, one quick thing I wanted to ask. In slide 14, you have a plot where it looks like there are two anti-crossings. So
Yeah.
Just wondering what the second one is.
So this is just a high order magnon mode in the X-sphere. Yeah,
Like a non-uniform mode?
Yeah, exactly. This is always the
Mhm.
case. It's inevitable to have high order magnon modes, but usually these high order magnon modes have a weaker coupling with the cavity because of the mode symmetry. And actually using X-spheres, we can suppress high order modes to get to show up in the spectrum. If we use thin film devices, we will have more high order modes. The spectrum will be even more complicated.
Yeah. Okay. And one more question from Shen in chat. You have shown tuning of a magnon mode, coupling strength. Is it also possible to change the cavity mode in real time?
That's a very nice question. In principle, yes, but that will require quite complicated designs or integration with other materials. Say, for example, if you put piezo, I mean, you don't even need a integrated piezo device. You can put use a piezo stage to control, say, the shape of the 3D cavity. That's one way of doing that. Actually, I think people have done that even for low temperature devices in the cryogenic environment. But it's definitely possible, but it's a little bit complicated. And I mean, different from magnon, because in magnonics, the magnon tuning is quite simple, simply by changing a bias-magnetic field. So actually, in superconducting devices, this might be easier because there people have developed a lot of ways in controlling the superconducting resonator, even qubit circuits. For example, by using squid. That's definitely possible, but that also requires some additional design efforts, and it's not straightforward, but definitely doable.
Okay, thank you. All right, so it looks like we're out of questions, so we'll thank Xufeng again. It was a very nice talk.